Imagine you throw a ball at a wall with two holes in it. The ball goes through one hole or the other, left or right. It cannot go through both. That's obvious, right? Things go one way or the other, not both at the same time. Now let me show you something that completely breaks that intuition. Take a tiny electron. Simple. A particle. You fire it at a barrier with two slits, just like the ball, but at a microscopic scale. The electron has to go through one slit or the other, left or right. That seems logical. But when you actually do the experiment, when you really do it, you discover something completely insane. The electron goes through both slits at the same time, left and right, simultaneously. And here's the part that really messes with your head. If you place a detector to see which slit the electron goes through, if you try to look, the electron changes its behavior. Suddenly it goes through only one slit, as if it knows you're watching. This is not philosophy. This is not a metaphor. This is literally what happens. And this is the most important experiment in all of quantum physics. Because if you understand this, if you really understand what's going on here, you understand the central mystery of quantum mechanics. And honestly, even after decades of thinking about it, it still feels deeply strange to me. But it works. The predictions match the experiments, so we have to accept it, no matter how weird it is. Let me show you how this experiment works, and why it changes everything you thought you knew about reality. Let's start with something simple. Water waves. Imagine a pool. You create a wave. It travels across the water. Simple. Now put a barrier in the middle with one opening. The wave passes through the opening and spreads out on the other side. You see a circular wave pattern. Okay. Now, put two openings in the barrier, side by side. The wave reaches the barrier, passes through both openings, and on the other side, you now have two sources of waves. Those waves overlap. In some places, they add together. In other places, they cancel out. You get an interference pattern, alternating bands of high water and low water, peaks and valleys. That's interference. It's what happens when waves meet. And it's a clear signature of wave behavior. Now, let's do the same thing with particles. With little balls. You have a machine gun firing tiny balls at a wall with two holes. Some balls go through the left hole. Some go through the right hole. On the other side, you place a screen that records where they land. What do you see? Two piles. One pile behind the left hole. One pile behind the right hole. The balls that went through the left hole form one pile. The balls that went through the right hole form another. No interference pattern, just two piles. That makes sense. Balls are particles. They go one way or the other. Okay, now the real experiment. Electrons. You take an electron gun. You fire electrons one at a time at a barrier with two slits. On the other side is a screen that records where each electron lands. Question: what do you expect to see? If electrons are particles like the balls, you should see two piles, one behind each slit. But that's not what happens. What you see is an interference pattern, alternating bands, places where lots of electrons land, places where none land, exactly like waves. Wait, what? Electrons are tiny particles with mass and charge, yet they're interfering like waves. Okay, maybe electrons are waves. Maybe they spread out, go through both slits, interfere with themselves, and create the pattern. But here's the problem. You're firing electrons one at a time. There aren't many electrons present to interfere with each other. It's just one electron. You fire one. It hits the screen. Then you fire the next. And still, slowly, electron by electron, the interference pattern builds up. Each electron arrives at a single point on the screen. Click, a particle. But after thousands of electrons, the overall pattern is interference. So what is the electron interfering with? It can't be other electrons. There are none. The only possible answer is that the electron is interfering with itself. It goes through both slits at the same time, like a wave splitting, passing through both paths, meeting on the other side, and interfering. But when it hits the screen, it arrives as a particle, a single point, not smeared out. So what is the electron? A particle or a wave? The answer is both, and neither. It's something stranger than anything we have words for. It behaves like a wave while it travels. It behaves like a particle when you detect it. Okay, but now comes the truly crazy part. You said the electron goes through both slits. How do you know? Let's check. Put a detector at each slit to see which one the electron goes through. You fire an electron. The left detector clicks. Okay, it went left. You fire another. The right detector clicks. It went right. Every electron goes through one slit or the other. Never both. Now look at the final screen. What do you see? Two piles. No interference. Wait, what? A moment ago, without detectors, there was interference. Now, with detectors, there isn't. What changed? The only thing you did was look. You didn't push the electron. You didn't block it. You just observed it. And that was enough. When you don't observe, the electron behaves like a wave. When you do observe, it behaves like a particle. Your choice to observe or not determines what the electron does. This drove me crazy when I was young. I asked my professor at MIT, "Are you telling me the electron knows when I'm looking at it?" He looked at me and said, "I don't know, but yes. The outcome depends on whether there's a detector or not. And that's ridiculous." And he was right. It is ridiculous. But it's also true. I've thought about this for decades. I've done the calculations 1,000 times. It's still strange, but it's real. Now let me explain what's actually happening, because there's a lot of confusion here. People hear observation changes the result and think consciousness is involved, that your mind somehow affects the electron. That's nonsense. It has nothing to do with consciousness. To detect which slit the electron goes through, you have to interact with it. You have to scatter a photon off it, or do something physical. That interaction changes the quantum state. Before the interaction, the electron is in a superposition, a combination of went left and went right. Both possibilities exist simultaneously in the wave function. When you measure, when you interact, you force the electron to choose. The wave function collapses. Now it's definitely left or right. Once it's no longer in both paths, it can't interfere with itself. That's why the interference disappears. Not because of your mind, because of the physical interaction required to gain information. But here's the deep question. Before measurement, which slit did the electron go through? The standard quantum answer is neither. It went through a superposition of both. That sounds impossible, but the interference pattern proves it. If the electron had really gone through only one slit, even if you didn't know which, there would be no interference. But there is. That means something went through both slits and recombined. And that something is the electron's wave function. Now let me tell you how I like to think about this. Instead of thinking about wave function collapse, I think about all possible paths. Every possible way the electron could go from point A to point B. Straight paths, curved paths, paths through the left slit, paths through the right slit. Every path has an amplitude. To find the probability of the electron landing somewhere, you add up the amplitudes of all possible paths. Most cancel out. Some reinforce. The ones that survive determine where the electron is likely to appear. With two slits open, Paths through the left and right interfere. With detectors, you eliminate paths. That's why interference disappears. This way of thinking, summing over histories, is incredibly powerful. It's how I solved problems in quantum electrodynamics. That's why I got the Nobel Prize. Not because I explained what electrons really are, but because I found a way to calculate that works. And it works unbelievably well. We've done this experiment with electrons, photons, atoms, even large molecules like fullerenes. 60 carbon atoms. They still interfere with themselves. The predictions match experiments to absurd precision. So yes, it's weird. Yes, it violates intuition. But it works. And that means this is how the universe actually works. The double-slit experiment isn't just strange. It's a window into reality itself. And what it shows us is that the universe is far stranger, richer, and more beautiful than we ever imagined. And once you truly understand that, you'll never see the world the same way again. And it works unbelievably well. We've done this experiment with electrons, photons, atoms, even large molecules, like fullerenes. 60 carbon atoms. They still interfere with themselves. The predictions match experiments to absurd precision. So yes, it's weird. Yes, it violates intuition. But it works. And that means this is how the universe actually works. The double-slit experiment isn't just strange. It's a window into reality itself. And what it shows us is that the universe is far stranger, richer, and more beautiful than we ever imagined. And once you truly understand that, you'll never see the world the same way again. So let's take a step back and really think about what this means. Because it's easy to hear all of this and just say, yeah, quantum mechanics is weird, and move on. But if you slow down and actually absorb what the double-slit experiment is telling you, it completely rewires how you think about reality itself. In the classical world, the world you grew up in, objects have properties whether you look at them or not. A ball has a position. A car has a speed. The moon is there even if nobody is watching it. Measurement just reveals what was already true. That assumption is baked so deeply into our intuition that we don't even realize we're making it. Quantum mechanics breaks that assumption at a fundamental level. At the quantum scale, properties are not simply waiting to be discovered. They are not fixed in advance. They are encoded in probabilities, in wave functions, in superpositions of possibilities. And only when an interaction occurs, only when information becomes available, does one of those possibilities become real. That's not a limitation of our knowledge. That's not, we just don't know enough yet. That's what the theory itself says, and more importantly, it's what experiments force us to accept. You might want to say, okay, fine, but this is just electrons and photons, tiny things. Surely this doesn't apply to the real world. But that line between the quantum world and the classical world doesn't actually exist in the way you think it does. The only reason you don't see interference patterns when you throw a baseball is not because the rules change, but because the effects become unimaginably small and fragile. A baseball interacts with trillions of particles in the air, with light, with heat, with the environment. Its quantum coherence is destroyed almost instantly. The wave-like behavior is still there in principle, but it's washed out so completely that it becomes irrelevant. In other words, the classical world isn't a different world. It's the quantum world with the weirdness averaged away. And that should make you uncomfortable because it means the everyday solidity you experience is not fundamental. It's emergent. It's a statistical illusion built on top of something much stranger. This is why the double-slit experiment isn't just a curiosity you learn about in physics class. It's the simplest experiment that exposes the core of quantum reality. Everything else, atoms, chemistry, semiconductors, Lasers, MRI machines, even the stability of matter itself rests on the same principles. And yet, even today, physicists still argue about what it all means. Some say the wave function is just a mathematical tool, nothing more. Others say it's a real physical object. Some say all possibilities exist simultaneously in branching universes. Others say hidden variables determine outcomes behind the scenes. And the uncomfortable truth is that, so far, no experiment has been able to tell us which interpretation is right. They all make the same predictions. They all give the same answers. They all work. That tells you something profound. Maybe our demand for a single, intuitive picture of what's really happening is the wrong demand. Maybe nature doesn't owe us a story that fits neatly into the categories our brains evolved to use. Richard Feynman once said that nobody really understands quantum mechanics. And he didn't mean that physicists can't use it. We use it incredibly well. He meant that we don't understand it in the way we understand throwing a ball or pushing a box. There is no deeper classical explanation hiding underneath. Quantum mechanics isn't strange because we're missing a piece. It's strange because reality itself is strange. And the double-slit experiment is the clearest proof of that. A single particle traveling alone, exploring multiple possibilities at once. A pattern emerging only when you refuse to ask which path it took. Reality responding not to what you know, but to what can be known. Once you truly accept that, you can't unsee it. Every solid object around you is held together by quantum rules that don't behave like common sense. Every chemical reaction, every electrical signal in your brain, every atom in your body obeys the same principles that let an electron pass through two slits at once. You are not made of tiny billiard balls. You are made of probabilities, of amplitudes, of quantum fields fluctuating beneath the surface of certainty. And yet, somehow, out of all that uncertainty, the world we experience emerges with astonishing reliability. Chairs don't randomly dissolve. Walls don't blur into waves. The universe is weird, but it's also incredibly stable. And that balance between radical uncertainty at the deepest level and order at the scale we live in is one of the most beautiful things physics has ever revealed. And that realization changes how you listen to the universe, because once you know this, once you've seen that at the most fundamental level reality is built from probabilities and not certainties, you stop expecting nature to behave like your intuition says it should. You stop demanding simple answers to questions that may not have simple meanings. You start to understand why physics, at its deepest level, is not about telling comforting stories, but about writing equations that match reality, no matter how uncomfortable they are. The electron doesn't care whether you find its behavior reasonable. The universe doesn't care whether the explanation feels satisfying. It only cares about consistency. And quantum mechanics is relentlessly consistent. Every time we test it, every time we push it to new extremes, every time we build more precise experiments, it keeps giving the right answers. Not approximately, not sometimes, but with absurd precision. So maybe the lesson of the double-slit experiment isn't just that particles can act like waves, or that observation matters. Maybe the deeper lesson is that reality is not obligated to fit inside the boxes our minds want to put it in. At the smallest scales, the universe doesn't choose a single story until it has to. It allows possibilities to exist side by side, interfering, canceling, reinforcing, shaping outcomes long before anything becomes definite. And we, made of the same quantum stuff, are part of that process. Not separate observers standing outside reality, but physical systems interacting with other physical systems, participating in the same strange rules. The double-slit experiment is simple, but what it points to is not. It's a reminder that beneath the solid surface of the world you know, there is a deeper layer, one that is subtle, probabilistic, and profoundly unintuitive. And the more you look at it, the clearer it becomes. The universe is not weird because we don't understand it yet. It's weird because this is how it actually is. So the next time you hear someone say, quantum mechanics is just theoretical, remember this. Without it, your phone wouldn't work, your computer wouldn't exist, and chemistry itself would fall apart. This isn't speculation. This is the most tested, most accurate framework in the history of science. It just happens to describe a universe that is far stranger than we ever expected. The double-slit experiment doesn't just challenge how particles move. It challenges how reality itself comes into being. And once you understand that, once you really let it sink in, you realize that the universe is not only more mysterious than we thought, it is more mysterious than we can think.